All right. So hello. So yeah, for today we're going to do 16.9 and 16.11, and Monday, and we will continue 16.11 to Monday, and on Monday we'll at least start 16.12, and I think probably a week from I think a week from today I'll at least start indulging myself and talking a little bit about some stuff related to my research work, and but there is an excuse. It will actually be sort of related to it will also be related to Galois theory in a way that you'll see. Anyway, so the take-home 3 is I haven't written it yet. I guess I better write that tonight, and I will get that out to you tomorrow. But again, so it's in principle due on Monday, but again, all deadlines are elastic. Oh yeah, and today is DJ, and for those, I think those of you who missed it, which I think is most everybody, was me. Oops. Let's see if I can get over here. Yeah, there we go. So yeah, I started with a little Sultans of Swing, which I wore out. Like I played that so much when I took this course. So I guess it's a little bit of a nostalgia thing. Music I actually sort of associate with taking algebra from Artin back in the day. Anyway, okay, so let's see, where were we? Well, let's summarize. Yeah, well, where were we? Let's summarize where we were. Okay, so suppose K is an extension of F, and it's a splitting field of the irreducible little f in big F bracket X. Galois theory, remember, relates to the field theoretic properties of K as an extension of F, and the group theoretic properties of G, the group of F automorphisms of K, the group of automorphisms, field automorphisms of K, fixing F. In particular, we know that in this circumstance where F is irreducible, that G permutes the roots of F. It just sort of mixes them up in some way, but is therefore isomorphic to a transitive subgroup of Sn, where n is the number of roots of F, and n is the degree of F. So the main theorem of Galois theory says, that's that sort of double lattice thing that we saw before. The main theorem of Galois theory says that there's a bijective inclusion reversing correspondence between subgroups of G of the Galois group and oh my God, I will never remember to do this. Oh well, I'll do that. I'll just sort of put this in every day. Yay, there we go. And intermediate fields L between F and K that sends on in one direction, it sends H to its fixed field K of H, and in the other direction sends intermediate field L to the Galois group of G, Galois group G of K over L. And remember, that's always a little bit, it's sort of it's like the top part that you take the Galois group of, and not the bottom part. In terms of the bottom part, if you remember how that picture went, that the extension L, if you look at L as an extension of F, then that extension is Galois exactly when the corresponding subgroup is a normal subgroup, in which case the Galois group of L over F, sort of down at the bottom here, is the quotient group G mod H. So today, and actually I guess we're sort of getting to the end here. So today, the immediate problem that we're going to spend some time on is given the splitting field K of little f, compute the Galois group of K over F. And the eventual problem, sort of our final goal, which we'll actually start to get to today, is when can you write the solutions? So here, I mean, this is sort of the motivating problem of Galois theory. The reason why Galois was what came up with this theory. The motivating problem was when is it that you can write the solutions, the roots of roots of that irreducible f of x, an expression using only kth roots. Yeah, that's the name, roots of the polynomial. But but this time only roots in the sort of normal sense, for like square roots, cube roots, fourth roots. If you can do that, then f is solvable by radicals, and we'll see how to one lovely way by the end of the course. We'll see one lovely way to prove that a particular equation, like a specific example, is not solvable by radicals. Oh, and so solvability, and let me see. I guess, just to be consistent, I'll try to make this purple, or roughly the same purplish, I don't know, the actual purple. Solvability starts with Kummer extensions. Yeah, so today we'll be talking, I hope a little bit, get to a little bit about Kummer extensions, and that's, there we go, extensions. Okay, so that's what we're doing. That's what we'll get to today. That has to do with our eventual goal of proving that the quintic is, or finding a specific example of a quintic that is not solvable by radicals. Okay, so now are there any questions? Okay, actually, are there any questions either about our summary of Galois theory so far, or about something in the homework? I think there might have been. I think there are a couple of questions in homework, especially given that we have. Oh yeah, I guess I should mention that we'll have a problem session Friday. We're going to discuss problem sets 7 through 10, outstanding questions, because you'll rapidly see that. Well, I haven't written the thing yet, but your take-home exam will be based on the homework, and so as always, and so you'll see that you'll probably want to go back and look at some stuff that you didn't get the first time. Okay. All right. So, are there any questions about either this summary or anything on the homework, anything on problem set 10, which was sort of due on Monday? Of course, all deadlines are flexible. Oh yeah. Okay. So here we go. All right. So let me add a new page here. Okay. So Ravi asks, Piazza says, right. So and Piazza says, I think that, okay. So what Ravi is, so let me blow this up and let's talk about this. There we go. So what Ravi is asking about, so on Piazza, I think Ravi's talking about the K is a splitting field of x squared minus 2 times x squared, x squared minus 3 times x squared minus 5. And so, right, and so we know that K is Q of root 2, root 3, root 5. And we know the degree of K over F over Q is 8, because none of these things are contained in the others. And let's see, yeah, because when you build this up one square root at a time, each time you still the new thing you add on still has degree 2. And so right, so the order of the Galois group equals 8. Okay, so right, so is everybody good so far? So Ravi, is that yeah, that's where we were. Okay, so right, and so now so G is isomorphic to a subgroup. So here's where we got to on the discussion of Piazza of so I'm going to use a weird little notation. So S of X is the symmetry group on X. So where X is some set, and so if X has n objects in it, then S of capital X is isomorphic to Sn. So is everybody okay with this S of X notation? A little strange here, but yeah, okay. Okay, so now, so G is going to be isomorphic to, this is, right, so we saw that, Well, for one, okay, so this is just sort of first off. So on the one hand, there we go. So on the one hand, we know that G must permute. Let me say this. Let's see. So, so on the one hand, G is isomorphic to the subgroup of the group of permutations of plus or minus root 2 and cross the group of permutations of plus or minus root 3, cross the group of permutations of plus or minus root 5. And this is because the action of G preserves the roots of distinct of the distinct irreducible factors of what I call it, F. I didn't call it anything. F of X. There we go. Right back to this again. Of F of X. Okay, so so we're good with that so far. Okay, then you just compare the order of the two groups. I mean that's very close to a spoiler for that. But so now you just compare the order of the two groups. We know the order of G, and we know the order of this triple product here. So, bada boom, bada bing. That's still mysterious. Oh, why? But why is G isomorphic? Oh, wait. Robbie, could you? I hate to record you for YouTube, but can you say out loud what your question is? I think that'll be easier. Just turn on your mic and do I have to unmute you? You might have to. You can unmute. Go ahead.
Why does it have to be isomorphic to a subgroup of S square root 2 minus square root 2 cross?
Oh, right.
Like there's yeah.
So so before, okay, this is a very important point. Here we go. So before, when we said that the action of G is faithful, that means that G is isomorphic to a subgroup of the full group of symmetries preserving those orbits. So is that the point that you were sort of concerned with? Yeah. So right. So and let me remind you the proof of faithfulness. Proof of faithfulness of the representation. If an element of G fixes all of the roots F, we already know fixes Q by definition. Know by definition of the Galois group of K over Q that it fixes Q, so it must fix all of K, and it's therefore a trivial automorphism. So does that make sense? So yes, that's a very important point. That all right. So Ravi, we answered your question. Yes. Okay. That was a super important point. There we go. So any other? We have some. We got nothing but time, sort of. Yeah. I mean, we have like sort of. I sort of end up scheduling 2 Slack days, so we got nothing but time. Any other questions about this or about the homework or anything else? Okay then. All right. Let's get back to the quartic. Okay, so I think, and we actually got this is going to overlap somewhat with what we did last time, but that's fine. So just to review the transitive subgroups of S4, they are, the first 4 are the ones that always show up for any degree: the full symmetric group, the alternating group, A4, the dihedral group, D4, and the cyclic group, C4. Right. So this is remember the dihedral group is the symmetries of a square. This is symmetries square, which I remind you is going to be coming. You may remember is going to be important in a minute. And then there's one unusual, only for n equals 4. The sort of last class of an isomorphism, of a transitive subgroup of S4 is the Klein 4 group, which is is just exactly these permutations. And you can sort of by brute force see this is, well, one goes, there's something sending one to everywhere, and so this is a transitive subgroup. All right. So the question was, oh yes, and this is wrong. Oh my God. So you actually, this is wrong. And let me fix this. So given an irreducible quartic polynomial, which of these groups is Galois group? We can actually complete. So actually, I told you the first time I taught to this extent. We can complete these results by computation, but I should say, but one case is complicated to describe. But in one case, computation is complicated to describe. Oh yes, is this a good time for my? Yes, this is a good time for my digress. I'll send out a reference about this later. So I wanted to sort of fill in 2 things that I looked up after last time. So here are 2 points I looked that I actually went in Google last time after we got done on Monday. So the first is there are methods for computing the Galois group there. So given a polynomial, there is in principle a method. There is a method for computing the Galois group of K over F. So there is. I mean, and in fact, this is due to Jordan, as in Jordan canonical form, from 1870. In the general case, but they are not practical, even with computers. I think I can't remember. Well, anyway, beyond some sort of small degree, those methods start to fail. So there is at least in principle there is a method for you can do it. You can just sort of just sit there and beat it to death by brute force and say, well, if these are exactly the these are, so Robbie was asking, Robbie and Meng Ruins in some slightly different form. We're both asking last time, well, if you how can you tell whether even permutation is part of the Galois group? And you can. There is Jordan worked this out was like 150 years ago, but in practice the computation is too burdensome to finish. And let's see. Oh yes, and so the inverse, and looking this up, the inverse Galois problem over the base field which is C parens T, the field of rational functions in one variable, is solved essentially by Riemann, and that's like late 1800s, using essentially before this is actually before the word was invented. Let me say inverse Galois. I'm going to go with the word problem just so I can fit this all in one slide. With analysis plus topology. What? That Riemann was a tricky person, huh? Anyway, right. So there, the answer is actually, I think this first question is something that Ravi and Monroe were asking about, that there are methods for computing the Galois group in general. They're just not practical. They sort of break down even with computers. And the second thing, which is something I thought, I can't remember how this goes, but I looked it up. The inverse Galois problem, if you start, instead of starting with a base field of the rationals, if you start with a base field of the field of fractions in one variable with the coefficients of complex numbers, that was actually solved by Riemann. And the proof involves like there's how does this go? Well, so there's one part which I know, which I understand, which involves like doodly pictures and cut and paste. And as you'll see when I start to indulge myself, like basically my research is all doing with doodly pictures. But then there's a way to sort of bridge that. You can take those doodly pictures and then sort of somehow turn them into analysis, which is an amazing thing, which I don't understand. And actually, I would really like to understand this. I've tried to understand this in the past, but I've never gotten the hang of it. This would make a great master's thesis if somebody wants to learn this. So you need to know a little bit of analysis. I mean, you need to know a little bit of everything. There's some cut and paste geometry. You can call it topology, but it's really just it's the mathematical equivalent of it's like mathematical kindergarten. It's like scissors and tape. But this would make a great master's thesis if somebody wants to understand this, and then you can sort of, and then you can really take it quite far. So anyway, if somebody's interested in that, that's a great expository master's thesis. You could tell somebody at some later stage, and if you wanted to apply for a PhD program, you say like, well, I learned about the inverse Galois theorem over C of T, and they go, oh, okay, that's like real math, man. Anyway, just so you know, it's not an attractable open problem. This is still an open problem in general, but it would be an interesting master's thesis to sort of talk about that. Anyway, so there's the resolution. I'll send you references when I remember. I have it down on my to-do list, but I did want to resolve those questions from last time. Okay, sorry, that was quite a digression. So anyway, are there any questions about the list of transitive subgroups of S4? Did I turn my camera off? No, my camera's still on. Actually, I'm going to try turning it off and turning it back on and see what happens. Yep. Okay. All right. So let's go on. Oh yes, and this is where we picked up last time. I improved the topography, but it's still not great here. All right. So so the special case of a quartic with only even degree terms, which means that's an irreducible where the roots are the form square root of r plus square root of quantities r plus root t, and you sort of stick in all the sort of possible all the plus and minuses on the inside and plus and minuses on the outside, which I forgot again. That's the trouble where if I just copy my notes from last time, I never fix the typos from last time. Oh well. Anyway, so right, so we have roots of that form. We vary the pluses minuses on the inside, varies on the signs on the outside. So G preserves the square whose diagonals are plus or minus alpha and plus or minus alpha prime. as we saw last time. So I wanted to draw. Anyway, let me remind you what that looks like. So this is the square whose diagonals are plus or minus alpha and plus or minus alpha prime. There it is. And so so this is every single if f is irreducible, then g is also transitive, and so we're down to these four possibilities, the subgroups of the dihedral group, D4, and each of the it just turns out by listing all the possibilities that each of these possibilities happens to contain the element rho, which is 180-degree rotation. That's what rho is. Right, so because it sends alpha to alpha minus alpha and alpha prime to minus alpha prime. So if you rotate the square 180 degrees, that we know actually just by group theory that G must contain that element, but it's hard to tell which other permutations are actually automorphisms of K. Okay, see, so still, or harder, I guess. It's maybe not that hard. Harder to tell, as we saw last time. All right, so let n be the group generated by rho, which is oh my goodness, which is again this terrible typography, permeates the permutation of alpha and minus alpha, and alpha prime transposes alpha and minus alpha, and alpha prime and minus alpha prime, and n. So that group fixes both the element alpha squared because we're just flipping the sign of alpha, and alpha prime because here we flip the sign of both of those. And if you square either of those, you get an element of f. And so if you just work out the how it goes over here. And so if L is equal to f adjoin alpha squared alpha prime, then we have this chain of this tower of fields. And so and we know that this has degree 2 because of the fixed field theorem, and we know that the whole thing has degree at most 8 by the main theorem, or degree dividing 8 actually. And so we can compute G by determining in general sort of what happens with by computing the degree of L over F and figuring out which elements send alpha to say alpha prime and so on. Let's see. Oh yes, and so so and here without going into too much detail, because I don't want to spoil the problems, but the idea here is that we use the fact that if you have sigma in G, that is an automorphism. So what we end up sort of doing is end up using the definition of automorphism. All right, so so the full solution comes from the problems in 16.9, and so let's do one case. Let's see. All right, so sorry, that was all like a kind of quick repeat, but we did it last time, so I don't feel too bad about repeating it. All right, so let alpha. So taking the example of x to the fourth minus 2. Let alpha be the fourth root of 2. And so the roots of that polynomial are alpha, alpha prime, which is I alpha, and minus I alpha. And so if we let L be f adjoin alpha squared, alpha prime, that's just computing. We get that's f adjoin root 2 and I root 2. And so the index the degree of L over f is 4. So if this degree is 4, then L has to be equal to the fixed field of n, and the whole thing must be actually equal to 8 and not just less than or equal to 8. And so the only possibility is G is equal to D4. And so here are the elements. Oh right, so let's start. So what I want to do is I want to draw the the subgroup lattice of G, and then sort of draw the accompanying intermediate, that sort of corresponding intermediate fields for K. All right, so all right, now finally, so let's say sigma is going to be the cycle alpha goes to alpha prime, goes to minus alpha, goes to minus alpha prime. And I want to note here, because in this particular case, there's a sort of, I don't know, I'll put that there. There's a better description of this. This is multiplication of the roots by I. Right. If so, as it happens here, yeah. So the roots are in this order: alpha prime, minus alpha prime. That's alpha I alpha minus I alpha. So this is the cycle of sort of rotating the roots around by multiplying them by I. And then I guess I guess we should pick a tau. So there are various ways to pick a tau. I can't remember which one Artin does, so oops. Actually, might be here anyway. Let me pick a tau. Let's see. So let's say it's the one that flips alpha and minus alpha. I think it might be different. It might be. I think it might be different in Artin, but we'll see. Okay. So all right, so now let's talk about the elements and subgroups of G. And I have to admit, this this you kind of have to plan out because it's mildly complicated. This is about the last case that you can kind of do. Well, not the last case, but it's sort of maybe one of the last cases where you can actually kind of actually draw the subgroup lattice in a finite amount of time. So I think so. Remember since we're going to draw this with the big field at the top and a little field at the bottom. Let me pull out for that. Oops. Question. What is tau again? Okay, so so remember, right? So where did I come up with that tau? Let me draw over here just. So the one way to think about this is that there. So so remember that we determined that G is exactly the symmetry group of this square, and so tau here it is that element. That's tau. Tau is a sort of flip. You can say it's flipping over this diagonal here. I'm just going to give myself a bigger pointer. It's flipping over this diagonal here, or you could say you're flipping this. You're flipping, not flipping over it, but you're actually just flipping this diagonal and preserving the other one. I think it's probably better to say you're flipping over the I alpha diagonal. Yeah, actually, let me insert a page here. Yeah, so I guess I should probably what I should do. Yes, this is what I should do. I should talk a bit about the symmetries, so the details of the symmetries of the square. So let me talk about that for a bit. So here's our square: alpha I alpha minus I alpha, and so we have sigma. We saw is rotation by 90 degrees, I guess, like this. So it's that permutation there. It's, that sends that permutes the corners in that manner. So sigma and sigma equals. Sigma is a permutation alpha I alpha minus I alpha. And we just saw that tau, right. So I think sigma squared is rho. That's a 180, the 180 degree notation, and sigma cubed. Those are also elements of G, and so those are not so hard to understand. So is everybody okay with the cyclic subgroup of D4? So good. Okay, so now let's talk about the reflections, and because 4 is even, there are actually two classes. So so there's tau. Right? I should say none of this is obvious. This is just sort of like, well, if you sit there and you study this for a while, this is what you get. Or okay, if you teach abstract algebra a number of times, you absorb this. So tau is equal to, it permutes alpha and minus alpha and leaves the other, it sort of flips alpha and minus alpha and leaves the other two fixed. And sort of not, it's true but not obvious that sigma squared tau, actually leaves, well, I mean, you can kind of see, it's important to note that sigma squared again is flips alpha and minus alpha and flips I alpha and minus I alpha. And so sigma squared tau so if sigma squared tau, that'll undo the flip of alpha and minus alpha, and we'll just flip only and we'll just flip only I alpha and minus I alpha. And so we have that permutation. That's sigma squared tau. Tau. All right, and there's two elements left. So those elements are maybe a little more complicated. Let's see. So, and I will have to, I'm just going to name one. So I'll draw them, and then I'll have to, so those are edge flips. So those are diagonal flips, and these are vertex flips, and these are edge flips. So there's one element that flips alpha and alpha prime, and then also flips minus alpha and minus alpha prime. And there's another element that flips alpha to minus alpha prime, and then flips minus alpha to plus alpha prime. And one of these is going to be sigma tau, and the other one is going to be, let's see, one of these is sigma tau, and the other one isn't. The other one is sigma cube tau. Sigma tau. So sigma tau sends, all right, let me pull out so you can all do this with me. Sigma tau sends alpha to I alpha, and then tau, sorry, no, blah. So sigma tau sends alpha to minus alpha, and then minus alpha to minus I alpha. So this is, I guess this is actually sigma tau, and this is sigma cubed tau. Right. Again, because tau sends alpha to minus alpha, and sigma sends minus alpha to minus I alpha, and we're composing right to left in the usual way. That must be this, and then this is this. Let's see. And so which one? Right. This is sigma cubed tau, and this is sigma tau. All right. So that. Who knew that D4 was so complicated, huh? You know, this is literally the first example that you do, the first interesting example that you do in, or maybe the second. I guess D3 is probably the first example. This is like the second example you do in 128A. I think it's interesting that, you know, there's still a lot of detail there to be mined, even at this late stage. Okay, so everybody good on D4? Okay, so right, this should be sigma cubed. Okay, so let's see. So now we have. Maybe I should do this a little. Well, whatever. Okay, so this is. So remember, we had this thing called n, this normal subgroup n, and that was generated by rho squared, and so we have n over here. So that's the rotational subgroup of order 2, and then we have the rotational subgroup of order 4, generated by sigma, and then we have down here. And remember, the full group is always at the bottom. So the small group is at the top, and the big group is at the bottom. And corresponding to that, so we're going to have two fields in between. Let's see. I guess we just saw that the fixed field of n had to be L, which is going to be the product of right. We saw that L is Q of root 2 I root 2. So it's Q of root 2 I root 2. And now, all right, and there's a smaller subgroup. There's a smaller field, which is preserved by I. Oh yeah, and so here's the sort of, yes. Okay, this is helpful. So finally we get to this thing where I keep referring to, like, well, you just use the properties. You just use the definition of automorphism. That's all it is, man. So let me point out that sigma of alpha is I alpha, and sigma of alpha of I alpha is minus alpha. And so sigma of I is equal to sigma of I alpha over alpha, right? And because sigma is an automorphism, this is equal to sigma of I alpha over sigma of alpha, which is equal to minus alpha over I alpha, which is is I. So sigma fixes I. There we go. So does that make sense? Okay, that was actually useful. That one was actually quite useful. So does that make sense when I say what I mean when I say, well, you just use the properties of an automorphism? Any questions about that? Okay, and so sort of in a not obvious way, Q of I is a subfield of K. Is a subfield of, so that somehow when you have all the roots, the splitting field of x to the fourth minus 2, then it turns out that Q of I has a sort of surprisingly important role to play in there. Okay, let's see. So that's what sort of the cyclic subgroups look like. It's a nice sort of chain there. I think, I do want to finish up quartics today, at least. I think we might not get to the Kummer extensions today, but so let me sort of just do let me just do one side. So what happens? Yeah, so what's going to happen over here is that we're going to have a bunch of subgroups of order 2. Let's see if I can remember how this goes. Yeah, so what we're going to have here is we're going to have there's going to be a subgroup of order 4 here, and there's going to be 2 subgroups of order 2, the cyclic groups, and so yeah, you can tell that I'm not like doing this spontaneously. I have actually practiced this, God forbid. Okay, I guess so there are 4 cyclic subgroups. There's the cyclic subgroup generated by tau, and there's the cyclic subgroup generated by sigma squared tau. So this is sort of well, I guess I should say what I'm going to do here is I'm going to divide this. I think one good way to draw this. This is why you have to practice, because drawing these things is not easy. This is sort of the diagonal flips side. And over here, we're going to have the edge flip side. And what happens is you have a sort of you have sort of the same structure on either side. This is going to be something like sigma tau and sigma cubed tau. And when you sort of combine these two groups, they actually combine to form a subgroup of order 4. This is the group generated by sigma squared and tau. And there's a group generated by sigma squared and sigma tau. So this is sort of so down here we have this group generated by one diagonal flip. And I guess sort of up here we have the group generated by 2 diagonal flips, which is the same as a group generated by one of the diagonal flips and 180-degree rotation. Same here for the edge flips. So this is sort of what this is the subgroup lattice. So okay, the correctness of this takes a long time to establish, and where I came up with this, well, I practiced. What we're getting, but given that this is actually correct, and it's not so hard, it's not so easy. It takes a while to sort of figure out. So let's assume this is actually correct. Does it make sense what I just said? At least but forget the process, because the process is long, and I'm just totally omitting it. Does the answer make sense? Like these are the subgroups of D4, and sort of like what the picture is saying, and kind of not necessarily where the picture comes from, but does the organizational scheme. So does that organizational scheme, assuming the answers are correct, which it is because I looked it up, does the organizational scheme make sense? Say yes. Or ask a question. Oh, I should circle the normal subgroups. There are 4 normal subgroups actually. So this is normal. Actually, they're mostly normal. Well, not mostly. I mean, there are more. So any subgroup of order 4, any subgroup of order 4 has to be normal. So the middle stuff is normal, but it's actually true that these other guys are normal as well. So so I should say green subgroups are normal. Yeah, that's not a. Oh no, I totally missed this. Oh no, I totally messed this up. Remember how I said that the inclusion reversing thing is very confusing? Well, that's true for me too. My bad. Let's try that again, shall we? All right, so edge flips. My bad. Okay, so sorry. So as I was saying before, I so rudely interrupted myself by screwing that up. Color coordination is very important. Okay, so there we go. 1, 2, 3, 4. So there are 4 subgroups corresponding to the flips, the cyclic subgroups generated by flips. So there's the diagonal flips that we saw, and then there are the edge flips, sigma tau and sigma cubed tau. Oh, that's a terrible 2. All right, so so those are the so those are the subgroups of order 2, and then there's when you combine them, you get corresponding subgroups of order 4, generated by sigma squared. And here we go. There we go. And sigma squared and sigma tau. And now this is correct. Sorry, my bad. right? So all the so again, as I was saying before, I sort of rudely interrupted myself. All the subgroups of order 4 are normal because they have index 2. I mean, vaguely remember there's something before about normal is index 2 subgroups are all normal, and so there we go. And so yeah, so there's that. So now that I've corrected it, and thank you for prompting me to draw the normal subgroups and correct my mistake. So now that I've corrected it, so does the corrected version make sense now? Say yes. I think I got it right this time. Okay, so let's see. So what is going to be? So let me just try to do one side, and it may take a little while. Right. So this is, let's see. This is degree 2. Yeah, degree 2 corresponds to index 2. So this is, so the things on this rank are all subgroups of order 2, which is index 4. And these are all subgroups of order 4, which is the same thing as saying index 2. Because remember the index of your subgroup is going to correspond to the degree of your extension. So let's just do one side, and I'll leave it to you guys to do the other side. Should we do the diagonal side or the edge side? Just somebody say in the chat. So it's index 4 on top because this trivial subgroup has index 8. I guess I got it right, yeah. And the bottom subgroup has index 1, right? So yes, it's very confusing. As if nothing, I think I just at least demonstrated how confusing the inclusion reversing nature of the Galois correspondence is. Okay, so should we do the edge side or the diagonal side? No takers? It doesn't matter. They're both the same. I'll do the diagonal side. Okay, so and now let me just, so I want something that's preserved by tau. Let's see. So by both tau and sigma tau. And sigma squared. So I want something I want an extension of order, a degree 2 extension, right? So this, whatever happens on at this level here is going to be degree 2. This is degree 1. Degree 1. Up here, this stuff up here is going to be degree. That's too high. Degree 4. Erase this thing, and then and of course there's only one extension of degree 8. That's the one on the top. I have to admit, you could kind of do these examples forever. They're kind of fun. Let's see. So so what else? Oh yeah, and I forgot. Oops, I forgot something here. N is contained. There's like 2 inclusions that I forgot, because N is actually contained in which is generated by sigma squared. It's actually contained each of those. So we need that inclusion as well. Because I was about to get a contradiction. Let's see. So we'll do the diagonal side just because it involves less because then I don't have to write I don't have to write the subscript as many powers superscripts. So hopefully it won't be quite as messy. So let's see. Tau sends alpha to minus alpha, and so does sigma squared. So both of those fix root 2. So this is, again, this is the diagonal side. Oh no, that's not what I want to do. Diagonal side. All right, so that's so that corresponds to sigma squared and tau, and so so I think, yeah, I mean, so there is something. It's going to be degree 2, and it must contain the square root of 2, and so well, there's only that limits it. So that's going to be q root 2. And you might, and as you can imagine, there's something sort of similar going on the other side. And then we have this inclusion over here. Let's see. So we need something that's preserved by oh yeah. So so we want something that's flipped. Right. So tau fixes I alpha and minus I alpha, and so I guess what we want is it's going to be q of I alpha. Is that right? No, that's over here. Okay. So so let's see. So we want an extension of degree 4. Oops. You know what? I'm going to cheat. No, I'm being silly. So one of these things. So I want this move. There we go. Okay, so let's see. So q adjoin root 4 must be here somewhere. And what is it that actually fixes alpha? Well, it's not tau. Oh yeah, it's going to be sigma squared tau. That's right. There we go. So I should draw that over here. Sorry. So hang on. Let me erase this. Oops. So q adjoin alpha is over here. That's a field between q root 2 and k and the full thing. So if and so that's going to correspond to sigma squared tau, because remember, sigma squared tau we saw fixes fixes alpha, and so we have that. And so there's something going to be similar. And I think I better not risk doing the rest of these cold, and so I will cowardly leave this as an exercise for you guys. So there's 4 other fields to fill in here. Yeah. Okay. Yeah, that'll be fine. All right. So are there any other questions? And let's see if I can, is there a way to, yeah, let me sort of pull out completely. Oh yeah, and sort of notice that, and let me circle in blue. These are the Galois extensions. Whatever that is. In blue are the Galois extensions. Okay. Yeah, I think I do want to get to finish up the general quartic. So are there any questions about that? And I think this is maybe something that, well, you and maybe I will have to stare at for a while. Oops. In quiet contemplation, but yeah, I think that'll be good. So, I don't know. Are we ready to give up on this for now, at least? Oh yeah, actually, and you know, I panicked. I panicked needlessly. I'm gonna be slightly less cowardly, and maybe and fill this in. Yeah, I just panicked for no reason. This is going to be Q of I alpha, because when you square that, you get minus alpha. That's fixed by sigma squared. That's fixed by tau, and so when you square it, and when you square that, you get minus √2, which is that's the same as Q of √2. So okay, that is in fact which generates the same field as Q of √2. So that is in fact a subfield of this. Okay. Anyway, yeah. All right. So let's move on. All right. Let's talk about the general quartic. And actually, so oddly enough, the general case is somehow, it involves computing some things that are not that easy to compute, because remember, computing these sort of invariants is not so easy. But once you have those invariants, it's actually fairly straightforward. So there are two things. There are two things that allow you to almost completely figure out what the Galois group of any general quartic is. They are the square root of the discriminant. This is going to be the square root of the discriminant and the resolvent cubic. Thus the name. Okay, so let's look at those. Okay, so let delta be, well, the square root of the discriminant. So you write down the definition of the discriminant. It's the discriminant, remember, is the product of all the alpha I minus alpha j's, where I and j are distinct, and so except all these squared. And for delta, you just sort of erase all the squares. And so that's something whose square is d. And as before, for exactly the same reason, an odd permutation of, I should say, in S4 sends delta to minus delta, and an even permutation fixes delta. And so if d is a square, which means that in F, which means that delta is fixed by your Galois group, then G, then your Galois group G is going to be either alternating or the Klein 4 group. Otherwise, G is going to be S4, D4, or C4. And so the same thing happens for any degree. So this is exactly the same thing we saw before. Actually, this isn't quite so easy to read. So let me just write in G. G equals G. Oops. All right, so exactly the same proof that we saw with in degree 3. Exactly the same result. So there is, in general, the square root of the discriminant allows you to distinguish between Galois groups that are fully alternating or sort of have at least one odd permutation. So that makes sense, I hope. Good. Yeah, but though as we saw from your homework, it's not that easy. That you can sort of beat it to death, but it's actually not that easy to compute the discriminant. But it's something you could do on a computer, for example. Here's something that's very special to degree 3, degree 4, the resolvent cubic. So I can't. So one of those French dudes, and so I had this problem where I only remember people's names by the sort of the first initial, and so all the great French mathematicians of like the 1700s and 1800s, I mixed them all up because they're all Le something. Anyway, this is Le somebody. The resolvent cubic. And so if we choose to do this very clever thing, let beta sub alpha be beta sub a be alpha 1, alpha 2 plus alpha 3, alpha 4. And right, so this is, so again, this was alpha 1, alpha 2, alpha 3, and alpha 4 are going to be the roots. I think this is by now natural because we've done this often, but just in case, when alpha 1 alpha through alpha 4 are the roots of our irreducible f, if you take this combination of the roots, it just so happens that that each of this corresponds to this little bit of combinatorics. It shows up in a lot of different ways when you have 4 objects, but 1, 2, 3, 4. So this just happens to be the every possible. You also see this with the Klein-4 group, right? This happens to be every single way of grouping 4 objects into 2 groups of 2, and there's 3 of them, and so that is invariant. That's invariant under permutation because there's only because this is the set of every way to do it, and so the permutations of if you permute the alpha I, then beta A, beta B, and beta C are preserved, and so the coefficients of G, actually type this. It's even faster to erase this and type this. So the coefficients of G are symmetric functions invariant essentially of symmetric functions are functions of the alpha sub I invariant under S4, which means that they're equal to a polynomial combination of symmetric functions of the alpha sub i's, which means they're equal to some sort of polynomial combinations of the coefficients of our original polynomial f. So the point is, so g of x is in f. Coefficients are in the ground field. So g of x is a polynomial, and is computable by some complicated formula. So for example, for example, one of the terms. So if you look at g of x, and like one of the terms isn't so complicated. G of x is going to be like x cubed plus minus beta 1 beta a plus beta b plus beta c x squared, and plus more complicated stuff. And that is exactly, if you look at it, this is exactly all the ways of pairing two elements of two of the alphas, and so that's actually symmetric polynomial number 2. That's actually S2, and the others are more complicated. Right, not the also the beta sub A and beta sub B and beta sub C are distinct. That's here's a cute thing. So let me just do beta A minus beta C. That's going to be equal to 1, 2, 3, 4, and 1, 4, 3, 3. Alpha 1, alpha 2 plus alpha 3, alpha 4 minus alpha 1, alpha 4 minus alpha 2, alpha 3. And so let's see. And the cute thing is that you can factor all these things, and let me show you how. The cute thing is that let's see. So what we want to do is we want to have alpha 1. So we can factor any such expression because as we put one of those terms, we put the first term in the plus part and the second term in the minus part. And so if I put alpha 3 and alpha 4 over here, I'll get alpha 1, alpha 2 plus alpha 3, alpha 4, and then I guess I just have to match make the minuses work out correctly. I guess this is alpha 4 and alpha 3. Ta-da! Look, it works. So you can FOIL that out and see that it works. Right. So this is not 0, and this is not 0 because the alpha sub i's are distinct. Right. Right. So G has distinct roots. And so, because remember, f is irreducible, and the alphas are the roots of an irreducible polynomial. And because we're in characteristic 0, the roots of an irreducible polynomial are all distinct. Whew. Okay, and so now, right. So if we have some G in S4, and we happen to look at this particular subgroup, which is the Klein-4 group, then Gx trivially on each of beta sub A, beta sub B, and beta sub C. I'd leave that up to you. Exercise, because I know I have 0 minutes left. The action of G is, why did I form this G mod G intersect K? Well, that's because that's the action of G on the betas. And so G mod G intersection K is isomorphic to some G bar, which is a subgroup of S3. Right, and there are 3 cases: either G splits in F and G bar is trivial. So it's because if G splits completely, if each of beta A, beta B, and beta C are all in F, then they're all fixed. They all have to be fixed by G, and so G is going to be equal to K, and so that's the only solution. That's the only possible solution. If G has one root, then one thing in F. So remember, the things in F all get fixed. Then beta sub C is fixed, and so G bar has to be has to permeate the other two, flip A and B, and so G is going to be equal to either. Right, I guess I should say G is a subgroup of. My bad here. Is a subgroup of the group flipping A and B, and so either G is C4 or D4, and then finally, if G is irreducible, then G bar is equal will be either A3 or S3, and so G must be either A4 or S4. Okay, and so I guess I can actually even do this. So let's see. So D is a square, and D is a non-square, and G is irreducible, and G is reducible. So if D is a square, let's see, how's this go? If discriminant is a square, then we get either A4 or D2, and And so here we have A4 and D2. And if D is a non-square, then the cases are if D is a non-square, then we have S4, D4, C4. And so if G is irreducible, then we get S4 and C4 and D4. Whew, sorry about that. And so so we can, just by computing, the point is, just by computing these invariants, which are not so easy to compute, but we can compute them, you can actually get it down to where there's at least at most one ambiguity, and this is more difficult. But you can compute that in general. All right, so thank you for your patience. Sorry about going over time by 3 minutes. Thank you.